Welcome back to Gradient Daily. Today we are breaking down a paper that delivers exactly what it promises on the cover, TripoSR. The central claim of this research is the generation of high-quality 3D models from a single image in under half a second. TripoSR is a joint research effort developed by Stability AI and Vast AI Research. They built a heavy-duty transformer model designed to solve one of the most computationally expensive tasks in computer vision. For years, generating 3D structures from 2D images meant relying on iterative NeRF optimization, a process requiring a model to guess, check, and adjust over minutes or even hours. TripoSR completes this process in less than half a second. Pushing inference time below this specific threshold has immediate utility. It unblocks real-time 3D asset creation for extended reality pipelines, allows developers to populate gaming environments on the fly, and enables dynamic physics simulations to generate collision meshes on demand. Moving the needle on inference time shifts 3D generation away from an offline post-processing task and turns it into a live, interactive runtime capability. The most interesting aspect of TripoSR is that it does not invent a completely new architectural paradigm from scratch. Instead, the researchers achieved this speed by taking the existing, well-documented Large Reconstruction Model, or LRM, framework and ruthlessly optimizing it. The paper details how the team drove a massive leap in both quantitative and qualitative performance through three highly specific pillars: overhauling the data processing pipeline, modifying the transformer design, and applying aggressive new training techniques. Furthermore, they achieved these optimizations entirely in the open-source domain. TripoSR is released under an MIT license, placing it in direct contrast with slower, closely guarded closed-source alternatives. Which brings us to the central technical question of this paper. How exactly does a feed-forward model bypass the standard iterative rendering loop without sacrificing geometric detail? As we look at the mechanics, you'll see that in modern AI research, major performance leaps often stem from strict architectural discipline and meticulous data curation, rather than foundational reinvention. Single-image 3D reconstruction is an inherently ill-posed inverse problem. The model receives a flat grid of pixels and must mathematically infer the missing depth and volume data. Traditional iterative optimization approaches this like a painter. The algorithm looks at the 2D input, paints a mathematical stroke into 3D space, checks the error, and continuously adjusts its work based on new observations. It is accurate but incredibly slow. A feed-forward framework like LRM approaches this like a master sculptor. The model analyzes the 2D subject once and instantly stamps out the entire 3D form in one continuous, unbroken mathematical motion. By utilizing learned priors from massive datasets, TripoSR processes all spatial features simultaneously to map the entire volume in a single pass, acting as an instantaneous CT scan for 3D objects. This is the large reconstruction model architecture that makes this single-pass generation possible. The pipeline breaks that single image apart into a sequence of smaller square patches, feeding them directly into a vision transformer, or VIT, image encoder. Inside the encoder, self-attention mechanisms process these patches to extract global context, mapping the relationships between the pixels to understand the overall shape and structure of the object. These processed patches are then projected into a triplane NeRF latent representation. This is the core mathematical bridge, a compact grid storing continuous volume and color data across three intersecting two-dimensional planes. Finally, a multi-layer perceptron decoder translates those latent planes directly into the final 3D wireframe mesh. Because this entire pipeline is an unbroken, single-pass feed-forward loop, there is zero iterative optimization required at runtime. That is the exact mathematical reason a 0.5-second inference time is physically possible. TripoSR relies on the transformer architecture to run this pipeline. Originally designed to predict the next word in a sequence of text, transformers are adapted here to predict dense 3D geometry. The model maps 2D image patch tokens directly into 3D spatial coordinates. This works purely because of the transformer's proven ability to scale its parameter count to handle incredibly high-dimensional mapping tasks. To improve this mapping, the researchers tweaked the model's design. They focused specifically on the attention layers, optimizing how the network queries the relationship between the 2D input tokens and the 3D output space. These modified attention layers force the model to prioritize spatial coherence across the entire object simultaneously, preventing it from generating fragmented or floating geometry. They paired this architecture with highly aggressive training regimes. By carefully tuning the learning rates and batch sizes, the team forced the network to converge on weights that guarantee sub-second inference speeds. A critical part of this training involved minimizing the rendering loss. The model was heavily penalized anytime its feed-forward 3D projection didn't perfectly match the ground truth target views. This scatterplot visualizes the result, mapping inference speed on the x-axis against geometric fidelity on the y-axis. You can see TripoSR sitting alone in the fast, high-quality quadrant, far outperforming early zero-shot models. Previous open-source models failed to achieve both fidelity and speed simultaneously because of computational bottlenecks. They either sacrificed resolution, optimized purely for speed, or sacrificed speed for detail. TripoSR's modified transformer architecture proves that real-time inference speed and state-of-the-art geometric quality are no longer mutually exclusive targets. The architecture, however, is only half the equation. The strict rule of garbage in, garbage out applies intensely to transformers. To train a model of this scale, Stability AI and VAST required massive, highly curated datasets, drawing heavily from large-scale 3D repositories like Objaverse. The absolute necessity here is aggressive filtering. Before a single weight is updated, the researchers had to strip bad, low-resolution, and non-manifold geometries out of the massive training pool. The remaining high-quality models are then systematically rendered from multiple camera angles. This creates perfect pairs, a single 2D view cleanly mapped to its exact 3D ground truth. The model learns universal 3D priors exclusively by absorbing these perfect, highly curated multi-view renderings over millions and millions of iterations. Achieving open-source LRM implementations have attempted similar architectures, but they failed to reach TripoSR's fidelity, specifically because they lacked this level of data curation. Stability AI achieved their qualitative leap by pulling specific data filtering levers, like strict texture and geometry thresholds, that their competitors simply ignored. The architectural tweaks to the attention layers we just discussed would mean absolutely nothing without this exact, unforgiving standard of data processing. While the code is open source, the model's competitive advantage resides in the proprietary, rigorous data curation pipeline used to assemble its training set. Achieving 0.5-second inference speeds requires making specific computational compromises. The model's core assumption is that the single 2D input view contains enough semantic information for the transformer to correctly guess the rest of the object's volume. The primary weakness is highly occluded or ambiguous geometries. If an object's defining features are hidden from the camera, the model will stumble. Because this is a strict single-image-to-mesh pipeline, the network is mathematically forced to hallucinate the unseen back half. This frequently results in blurred textures or incorrect physical structures. There is also a stark difference in reliability based on the input. The model performs perfectly on clean synthetic renders with white backgrounds, but fails far more frequently when fed noisy, in-the-wild photography with complex lighting. Before this model can be integrated into raw, unpredictable environments like live VR pipelines, researchers will need to conduct follow-up experiments on its robustness against background noise and poor lighting. While the LRM architecture is blazingly fast, its reliability remains strictly bound by the visibility and quality of the initial 2D input. This summary slide outlines exactly how TripoSR bridges the gap between speed and quality. First, TripoSR successfully achieves 3D mesh generation in under 0.5 seconds by utilizing an unbroken feed-forward LRM transformer architecture. Second, its superior performance over other open-source models stems entirely from rigorous optimizations in data curation and training regimes, rather than relying on a novel architecture. Finally, the model and its code are released under an MIT license, making it fully open source and ready for immediate deployment in research and commercial pipelines. This release democratizes state-of-the-art 3D generation. By removing the bottleneck of iterative rendering, it sets a powerful new baseline for the developer community. That concludes today's breakdown on Gradient Daily. Thank you for joining us for this deep dive into the TripoSR architecture. If you found this rigorous technical analysis valuable, please like the video, subscribe to the channel, and hit the notification bell. We read the latest AI research so you don't have to. We'll see you back here tomorrow for our next paper breakdown.